Good morning, everyone. Let's get started for today. So we have a couple slides. So these slides for today are in the chapter 1 through 3 review in the lecture slides module if you want to follow along. After just a couple slides talking about what we call metacognition and a few details about that, we're going to get into some review problems from the first 3 chapters. Of course, our first midterm is Monday night. Hopefully, we're thinking about studying for that this weekend if you need to do some final studying. I was just looking at the game time. Tomorrow's game's 4 o'clock, so I think that's great for those going to the game. Get to sleep in a little bit, watch some football, have some fun afterwards. And Sunday, after you watch the Browns, you can study for some chemistry or whatever NFL team you follow. So hopefully you can work something fun in over the weekend on top of just preparing for the exam. Practice exams are now posted on Carmen. There's PDF versions. I think there are also Carmen versions. Is there a Carmen version? Can anybody? Yeah. Okay. And the Carmen version by far is what I would recommend that you take at least one of, just to make sure that you can kind of get used to taking the test through Carmen. There should be some data entry questions so you can kind of see the flavor of those questions, just to be able to prepare for those. The test itself will be a completely different set of questions. I think the best way to look at a practice test is it's a way to assess how you might do on the real test. If you take the practice test and you get a 60%, that's not necessarily the worst thing in the world if maybe that's tonight or maybe early Sunday, so that you can have some time to look into the questions that you missed, the topics, do some more review, and kind of build up from there. But if we only do one practice test, we get a 60, and we don't do a whole lot of studying after it, my guess would be the real test we're going to get somewhere near a 60, because it's kind of just a snapshot of how you might do in the real test. Even if you just go through the practice test and find the problems you miss, how you solve those problems, you have to almost take a step back and say, how do you solve a problem like the one you missed that may not be the exact same type of problem? And even on the questions that you got correct, you might want to critically evaluate or try to maybe keep track of the ones you were kind of guessing on or not super sure about, so you can double check those topics as well. And so if you do that there's 3 practice exams, there's a bunch of daily quizzes that you can kind of go back through the different topics where you need more practice. If you haven't done a lot of those, I think that would be great practice heading into the midterm. So hopefully you take each practice midterm, get a little bit better each step of the way from extra review. Now, we were beginning to talk about metacognition last time. It's the idea of just trying to think about your own learning and being sort of actively aware and engaged in the learning process, and trying to use your own thoughts about learning. This is why a lot of times I try to come back to sort of things you probably heard about from high school, because if I can jar loose something you already know about, we can probably more easily build up from there, as opposed to learning everything from scratch. If everything we've taught in this class has been from scratch so far, like almost every word I've said in the class has been unknown to you, that's probably where I would say a lot of heavier reading would be helpful, even more than once, like reading through a chapter 2 or 3 times. If it's been 3-4 years since you've had high school chemistry, maybe you don't feel like you learned it that well the first time around. If when I've said things like, oh, you've probably seen this in high school, and you've been like, oh, don't remember that at all, that's where I'm thinking heavier reading is going to be more helpful, probably towards your learning. Or as we get into the class and we get into topics that are more far removed from things you've seen in high school or seen before and don't have that basis to build up from, I think that's where some of these metacognition skills can help us. So a couple recommendations from metacognition are like the power of preview. So sometimes it's helpful to preview material before you get to class. I think we're all probably still relatively fresh from high school from a lot of the concepts. So the previewing may just be recalling things from high school if you recall a lot of these topics. If not, I think skimming the material, the reading assignments before class can really be helpful for just setting the stage to preview what's to come within a given lecture. I think we're always going forward and backwards at the same time. So whenever we go forward with the material in class, usually there's something I like to review from the prior sections that's going into that problem. The same thing as you're doing your homework. We might push into section 3.4, but then have to review something from section 3.2 or 3.3 along the way. So we have to kind of always go forward and a little bit backwards with our learning. We have to get practice retrieving information. That's why I like the daily quizzes and recommend those. If you're taking the daily quizzes, you're getting sort of 2 things with those quizzes. You're getting retrieval practice if you close your notes and take the quizzes without any extra help. So you're getting that practice recalling information from your mind. That helps you learn things better. I often try to think, if you're trying to memorize a phone number or some key piece of information, probably the best way to try to remember it is to try to force yourself to write it down or to say it out loud, or just to recall the number and then double check it. as opposed to just like looking at a list and trying to memorize it. So our memorization is always like looking at a list and trying to memorize the list. That kind of works okay, but I think an easier way is to almost try to recreate the list. Or if you're trying to memorize definitions, which I think we're kind of beyond that at this stage, but if you're trying to memorize things like definition, maybe nomenclature, it's probably better to have like this, the formula, and then you're trying to say the name, as opposed to having your note card with the formula and name. So just trying to memorize formula and name together, force yourself to recall the name or the system or how it is that something has come to be named the way it is. That forced retrieval will help you learn and keep that information for a longer amount of time. Space practice is spacing out your practice. Space practice is doing, a half hour of work every day as opposed to 3.5 hours of work one day a week. So if you give yourself a chance to spread out your tasks, to retrieve information often, and have multiple small study sessions, I think you're going to find that you get more out of those sessions than you would a combined single learning session. And then lastly, self-assessing your own understanding. Like when you take a practice exam, like it's not easy to necessarily like check the key and see what you missed and then go back into the book to try to learn from your mistakes. That's not something that, I say it like it's easy, but that is a skill. And so you have to build that skill of trying to self-assess your learning, and then using metacognition to just what it is what you need to learn still, and how you put it all together as you continue through the topics. So this slide here was blurry for a second, is talking about previewing the material, attending class. I usually don't have to stress too much about attending class to you guys that are here, because obviously you value coming to class. That's great. Something I like to say is that as a course goes on, it's not abnormal for attendance to start dropping off. And the only downside there is, I understand the nature. It's 8 a.m., it's early, lectures are being recorded. But if you can continue to come to class, I think that's really good, because as the class goes, we get harder. The first 3 chapters, if you haven't been pushed too hard, I bet the next 3 chapters will push you pretty hard. Chapters 4, 5, and 6 that come up next are pretty tough. We're going to go through it as quick as we have chapters 1 through 3. So the information comes at us quick. We have to sort of stay caught up. I think the best way to stay caught up is just keeping up with that preview, either skimming the book or just recalling some things you know from high school, attending class. If you do miss class, just know that the videos are there. Try to watch them along with the class and not put off a lot of the lecture video watching until moments before the exam. Reviewing after class, this is where the homework assignments usually come into play to kind of push you into making sure we do some problems before the next class. But this could be a more thorough read before the next class. This could be doing a daily quiz or a couple daily quizzes before the next class. So there's a lot of things you could be doing in between class, and I think most of you guys are doing a lot of those things. Studying is a weird word. I mean, studying, I think, is often what we do when we haven't done a lot of the learning already. So when I say, oh, maybe we need to study on Sunday, I kind of hope a lot of you guys don't need to do a lot of studying. You might just need to do some touching up. You might just need to get some feedback in the case of a practice exam to see that you get a really good score when you take one practice exam, and maybe you don't even take the next 2. So studying, I think, is what we do when the other things kind of have fallen apart, or when we're putting together all the chapters that we need to know before a test. So studying, we could do this, but I think we need to think about all of these things here are also studying. So when we're reviewing, we're previewing, we're coming to class, those are all aspects of studying too. Assessing, I think that's the big one, is whenever we take a quiz, homework assignment, when we miss a problem, just ask yourself why, or ask yourself maybe there's a piece of content you were misunderstanding, maybe you had a misconception, or maybe you just didn't see something in the text yet in terms of reading that you could have read that would have helped you through the problem. I like to think that most of our problems, stoichiometry is a good example of this, stoichiometry is just like the balancing of a reaction, the molecules to molecules, or the moles to moles, and then we're just using those sort of ideas, those coefficients, those ratios to solve different kinds of problems. There's a lot of different stoichiometry problems. I have a few in the notes here today, but they're all solved with the same basic idea of there being some like mole-to-mole conversion using the coefficients in the reaction, or there's some molecule-to-molecule conversion from the reaction. So if we approach problems where we see the simple problem-solving step that we're using, the simple piece of material that we're putting into practice, then we can solve a wide variety of problems. I think you can understand the opposite. If you look at every problem you ever encounter as a unique problem, then we're like memorizing a lot of different ways to solve different problems when there was maybe just one key overriding concept that could have gotten us through all the different variations. So like Bloom's taxonomy, like this isn't, to me, a lot of teachers put this up. I'm sure you guys have seen this before. But the way I like to think of Bloom's taxonomy is if you want to, build knowledge and the ability to use knowledge, you have to start from the ground up. Like you have to learn simple concepts before you can put them into practice. So you have to learn some knowledge. You have to be able to comprehend that knowledge. You have to be able to apply it in simple problems before you can get into the process of like analyzing more complex problems. And where I think Bloom's taxonomy comes into play, and I see this a lot, this maybe is more of like a midterm 2 problem than a midterm 1 problem, but for midterm 2, where we have a lot of concepts that come at us fast, we have a lot of either review from high school going on or learning of new concepts or putting a lot of things together, if we don't do a lot of the preview, the learning, the reading, along with those chapters, we get closer to midterm 2. What often happens is you see all these problems on a practice test and you're like, oh, like I have to like learn how to do all these different types of problems, and we're missing the key pieces of concept, the key pieces of the course, where there's only a few key concepts that we're putting into practice on all those problems. If we just learn those few concepts, we could have solved all those problems. But if you jump into the problems and you start looking at all these analysis problems we give you, then you start thinking, oh geez, I have to learn how to do each one of those analysis problems, when really there's just a few key pieces of knowledge we needed to know. So if we start at the ground up, if we make sure that we're learning those concepts or putting them into practice in the simple problems, we can then apply them and analyze more complex problems as we go along. And so I just use this as a reminder that if you see a lot of practice exam problems or quiz problems that are just foreign, unknown to you, where do you even start these problems? Like that's where we go back to the beginning. That's where I say, well, we're going to go back and start skimming and like more thoroughly reading a chapter, and I think we'll then look at those problems later and see that they're pretty recognizable. Okay, so I don't know if I'm going to read through all of these, but these are just kind of like a list of strategies, like previewing the material before class, reviewing the notes before the next class, routinely doing end of chapter problems. I might say, for our class might be our lecture homework assignments on mastering. There are end of chapter problems. I would probably go do my daily quizzes before end of chapter problems. So my order of events would probably be, after class, try to do some reading, try to do the homework assignment due for the next lecture, maybe take a daily quiz, and then if I still want more problems, maybe then I'm going into the end of chapter problems. And I'm trying to get rid of my notes as quick as possible. The quicker I can solve a problem without extra help, the better, because that's the exam environment. That's really learning the concepts. How many of you guys plan on taking like a dental school, med school admission test, something like this, like a professional school? I mean, either we learn it now pretty solidly, we keep using this stuff when we get to OChem and other classes, and we don't necessarily lose it and have to relearn it, or we kind of struggle and then have to really like kick ourselves into high gear when we get to those tests where we want to do really well on those entrance exams to get us into med school, dental school, things like that. There's help available if you haven't gone to any office hours yet. My office hours right after class, 9:15 to 10:30 every day of the week. Stop by anytime. You don't need an appointment. There's the Learning Resource Center, so seek out help when you need it. Reworking problems. I think I'll just kind of leave the list here, but there's a lot of different strategies we can put into place. And I think the key would be you don't have to do all of them. If you're just doing the one that gets you towards assessing your strengths and learning from your mistakes and putting things together, as long as you're getting yourself to that stage, I think we're going to see good things in this class. Okay, 2 books I recommend. Probably this one I recommend more. This Make It Stick. This is a book that has a tremendous amount of examples on how to get better at taking like tests, get better at classes like chemistry classes. Has a lot of examples from cognitive learning. Specifically, there's a couple examples on students trying to get into med school and how they're studying and approaching learning. And it uses a lot of like real science in terms of like cognitive research studies that have been done on learning. Teach Yourself How to Learn is another book on like metacognition strategies. It's slightly more written for teachers than it is for students, but it's a book. If you hear this metacognition thing, you want to learn more about it, that's from this book here. Okay, so with all that, sometimes I sneak in, I have to talk about metacognition, so I'm kind of forced to give you those slides or things of the conversation we just had. But let's get into what we really want to talk about, which are some review problems that get us into some of the topics from the upcoming exam. So we have an example here. Sodium and chlorine reacting to form NaCl. Balance the reaction. and then determine the mass of NaCl that forms when we have these reactants combining. So I'm going to start with the reaction. Now, I was asked a good question before class in terms of like what physical states you need to predict here in reactions. I think for the most part, we're just kind of thinking for elements, trying to know that like the elemental form or the stable form of hydrogen's H2, N2, O2, Cl2. I don't know why I did F2 and Cl2 in a different order, but we have the two halogens, F2, Cl2. We have the noble gases of helium through radon that are atomic gases. By atomic gases, we mean gases that exist as just a single atom, not as a molecule. These here are gases, and I don't know if we would expect you to know all those are gases, but they're so common. You're going to see a lot of examples of like here, like Cl2 gas. If we had an example of bromine, and I don't know if they would expect that you would have this memorized per se. I wouldn't like the question, like, is bromine a liquid, solid, or gas at room temperature? I don't like the question because if you're in this room, you can just look and see that it's blue, meaning it's a liquid at room temperature. So it wouldn't be unfair, or it would be unfair to give this on a test and have some rooms with a periodic table that answer the question for you if you're savvy enough to look. But bromine's a liquid, I2 is a solid in terms of also existing as diatomic molecules. And then most of our other elements are either metalloids, which are mostly then solids like boron, silicon, phosphorus, arsenic, things like that. Those are all solids, but not metallic. And then all the other elements are solids and metallic, with the exception of mercury, of course, which is a liquid. And again, I don't know if I don't think we would put on a test as mercury a liquid, but you're just getting the sense that metals, like in their common state, would be like in the solid form. Other substances, I don't think we're predicting too much. Like CO2 is a gas at room temperature. I think we all know that. So I mean, I think some things are pretty obvious, but I don't think we would test you on like a combustion reaction. Is CO2 a gas or a liquid? You know, I think you should know it's a gas, but it's not something we tend to test you on. Okay, so when I write this reaction here, I have to make sure I balance it. If I'm going to do a stoichiometry problem, which it looks like I'm going to have to do, I should balance my reaction. So I'm going to need 2 NaCl's and 2 sodiums. It's oftentimes we might write a reaction like this and just write the Na plus Cl2 goes to NaCl and not think about the balancing. And then later we get to the mole to mole conversion step and we may not realize we didn't balance our reaction. So whenever we see a problem where, you know, it looks like we're going to have to solve a stoichiometry problem, just know that we have to balance out our chemical reaction. I also like to talk about common like things that you guys may think on a test that like a shortcut. Like everyone might take a shortcut here, or not everyone. Some students may be looking, you guys might be thinking, if I'm making this from combining these, well, isn't the mass just the sum of those two? Like, why wouldn't the mass of NaCl form just be the sum of the two? Well, the obvious reason why would be if one of them's in excess. So if one of the two reactants was in excess compared to the 1:2 ratio of chlorine to sodium we're supposed to have here, if one of the reactants is in excess, it's going to be left over, not converted into NaCl. Okay, so if we happen to have the 2 moles of sodium for every 1 mole of chlorine given to us here, then yeah, we could have added these up, but we have to check. We'd have to know to do that math. Now, in terms of solving this, we could go BCA chart. Maybe I'll show that first. I think this might be the only one I go through a BCA chart and like a dimensional analysis step just to make sure we're thinking of how to put into place a BCA chart. But to the BCA chart, I'm going to convert these to moles. So sodium is 23.00 grams per mole. So 23 grams of sodium would be a mole. And then chlorine's 35.45 times 2. So that would be about 70.9 grams per mole. So that's 1 mole as well. So I have a mole of each of my sodium and my chlorine, which is not the stoichiometric amount. So I definitely can't just add these up. If I saw here I had 2 moles of sodium, if for some reason this problem gave us 46 grams of sodium and 70.9 grams of chlorine, then I could just add those 2 masses up, and that would be the mass of NaCl. But in this case here, I need to work out which one of these two is going to go to 0. So which one of them goes to 0 and is completely consumed? Well, just think of it this way. If we consume all the chlorine, we need 2 moles of sodium, but we don't have 2 moles of sodium. So chlorine cannot go to 0, so sodium has to go to 0. Then I can apply my coefficients. This is the only reason I really like a BCA chart sometimes, is it gets us to think of the loss of sodium being twice as much as that of chlorine. So minus 2x for sodium, minus x for chlorine, just using the coefficients in the reaction to get the coefficient in front of x. And that lets me solve for x here, that 1 minus 2x is equal to 0. So I look over here and I can solve for x, that it's half a mole. So I subtract half a mole off from chlorine. If I wanted to see how much chlorine remains, I have half a mole of Cl2 that remains after the reaction completes. And then I will have formed 2 times x. So I will have formed 2 times half a mole, or 1 mole of NaCl. And then all I need to know is the molar mass of NaCl to convert into how much mass I get of NaCl. So 23 for sodium plus 35.45. The molar mass of NaCl is 58.45 grams per mole. So 1 mole of NaCl would be 58.45 grams. Call that 58.5 grams. Okay, so like I mentioned, we would show 2 ways on this one here. So the BCA chart, relatively useful. I think it's slightly more easy to set up a BCA chart if they just give us moles in the problem and not masses. Because if they give us masses, I have to convert to moles and I have to do calculations and write things down to start the BCA chart. So in this problem here on a test, I'd probably be more likely to say, well, let's just go through this problem here and figure out how many grams of NaCl I get if I consume all of the sodium. And then how much of the NaCl would I get if I consume all of the chlorine? And so I would just run through 2 stoichiometry problems kind of saying if 23.0 grams of sodium were to react in this reaction, how much product would I get? And then we can convert that to moles, 23.00 grams per mole of sodium. For every 2 moles of sodium that react, we get 2 moles of NaCl. And then 1 mole of NaCl is 58.45 grams. And so that would come out to 58.45. So 58.5 grams. And then for Cl2, 70.90 grams per mole of Cl2. For every 1 mole of Cl2, I get 2 moles of NaCl. And then convert them to grams. So that would be 117 grams. I mean, it's a choice. Like, in some ways, like a lot of times they turn these into data entry problems now instead of being multiple choice on exams. And like, there's good things and bad things when you have to type in the answer. The good thing is if it's saying to record, often when you see these problems on a test, they'll say record the answer to the nearest like 0 decimal places, and it'll say like example 25 to the nearest like whole number. It may say record to the nearest decimal place where it's 1 decimal place, so maybe to the nearest decimal place here. So like, let's say in the problem it's making you think the answer should be like to the nearest tenth of a decimal point. Well, if you're getting an answer 0.00452 or something, you did something wrong. You know, like you can usually tell by the magnitude of your answer if your order is a magnitude off from what would make sense to key into carbon, you probably want to double check your calculations. So it gives you a chance that if you're on the wrong order of magnitude, you can usually catch that mistake. When we give you multiple choices, if you just ran through, like, let's say this calculation here and got the 117 and see it as a choice, you'd go with it sometimes. And so sometimes a multiple choice test, we cleverly choose the answers to be the things you might have calculated that aren't the right answer in the problem and make them choices that trick you. And I don't really want to trick you into putting that answer. But if you didn't know to run through this step of the calculation and you really thought it should be 117, I want it to be available as a choice. And so sometimes multiple choices, you're not sure how to do a problem, so you think you calculate something that might be right, you see it as a choice, you're like, oh, okay, that's right. It's like, well, maybe it isn't right. So sometimes the multiple choices being there is actually makes the test harder. So anyways, I think probably enough time on this problem. 58.45 grams of NaCl, that's the mass of sodium chloride we get when we run out of sodium. We can't get to 117 grams because we don't have enough sodium to get there. Okay, let's look at this one here. So 5 moles of aluminum, excess oxygen to form Al2O3. What is the yield of the reaction if 185.0 grams of aluminum oxide is obtained? So we get this much aluminum oxide, but presumably we're limited here. We probably haven't gotten as much as we were supposed to get. So this is a problem here. We're going to use the percent yield is the actual yield divided by the theoretical yield times 100%, and then the actual yield is 185 grams. So 185 grams is our actual yield. We need to work through the stoichiometry to calculate the theoretical yield, the yield we should get according to the stoichiometry of the reaction. So I'd have Al plus O2 going to Al2O3. And so to balance, we go 3 and 2, and then a 4 in front of aluminum. Now, I like when we do moles, and it's usually my suggestion when we write exams that we just think moles, because you can think through the stoichiometry really easily. Like, you can look at 5 moles of aluminum reacting. For every 4 aluminums, we get 2 Al2O3s. So can you all agree pretty quickly that we should get 2.50 moles of Al2O3? That's our theoretical yield of Al2O3 in moles. And now, I mean, it's just to make sure if anyone isn't seeing how we're doing this, we're just trying to say the number of moles of Al2O3 is the 5 moles of aluminum that we're starting with. And then for every 4 moles of aluminum, according to this reaction, we get 2 moles of Al2O3. And then in terms of the theoretical yield, we probably want to divide a theoretical yield in grams by grams. So we just want to convert this to 2.5 moles of Al2O3 to grams. So we just want to go moles to grams. A lot of problems, like this is the standard notation that like ACS exams, if you took an AP exam, how many of you guys took the AP exam? So if you took the AP exam, you're probably seeing this notation of M equals. This is just the molar mass of this formula. So the molar mass of the formula, when you see the M equals afterwards, that's the molar mass. They specifically don't show you the units because the units could either be interpreted as AMU per single unit, per molecule, if you will, or it can be interpreted as the grams per mole. The grams per mole is what we can use here. So if we have 2.50 moles, multiply this by 102.0 grams per mole. And so 2.5 moles times 102 is 255 grams. So that's our theoretical yield. So that's the yield we should have gotten here if we got 100% yield. We only got 185. So that gives me 72.5% yield. So answer D. Now, sometimes we give you molar masses like this in problems, sometimes we don't. Like, often when we don't, like a lot of times like CH and O, like and N and things like, so common elements we expect you to know the atomic weights of, usually we'll leave off, especially on midterm 1, where part of the material is calculating the molar mass. So on midterm 1, you see a lot of problems will often have you calculate molar mass in the first exam when you need to do those. So expect probably not to be given every molar mass on a test that you need to calculate, where we want you to use your periodic table and make sure that you know how to do those steps. As we get later into the class, you'll see almost any time you need to do a molar mass on a test, we won't want you to waste the time doing that, and often we'll give you the molar mass. So let's look at the first question. So you have a compound with a molecular weight 4 times its empirical formula mass and has a composition of 88% C, 11.2% H. What's the molecular formula of the compound? Well, it's kind of funny. Like right off the bat, you can roll out A and B, right? Because those formulas are not possible, because if you imagine like CH2, that is an empirical formula. It is the simplest ratio possible for C to H for that formula. And if the molecular weight's 4 times that, that's just impossible. So it's impossible to have a molecular formula that's 4 times its empirical formula mass with the CH2 formula. And the same thing with C2H2, or whatever that is, C2H3, that would be impossible. C4H8 could be the empirical 4 times CH2, and then the D could be, it would be C3, C4, dividing both these by 4, so C2H3. So C2H3, or 2 times 4, 3 times 4 would be C8H12. So that could be an empirical formula too. So it's possible that the answer could be C or D. When you have a multiple choice test, if we're savvy sometimes, especially like imagine you're rushed for time, and this is your last question, and you have no time to use your calculator. Like everybody's like, or in Carmen a lot of times you actually have a timer, so it's not even the teacher calling time, it's the test literally ending. You have 30 seconds counting down, and you're like, oh, what do I go with? You could at least roll out half the answers. Now, in terms of how you would solve this from the data given, I would probably look at these masses here and relate the ratio of 88.8 grams of carbon to 11.2 grams of hydrogen. And then I'd be converting those to moles to get a mole ratio. So I'd go 12.01 grams per mole of carbon and 1.008 grams per mole of hydrogen. So it's 7.39 moles of carbon in ratio to, well, about 11 moles of hydrogen. 11.2 divided by 1.008 would be 11.1. And so, even, like if I'm pushed for time, I'm just going with D right now, right? Because it's not a 1-to-2 ratio. Like you can already kind of look and see that 1-to-2 would be 7.39 to 14.8-ish. And so how do we find specifically that would be C2H3? Presumably, let's divide by the smallest. That's one way to get towards a whole number ratio, is dividing by the smallest. We have to divide both by the same number. Remember, these are ratios, so I can't divide one by 7.39 and the other by 11.1 or anything like that. I have to divide both of them by the same number to keep the ratio of the masses to the ratio of the moles intact. And so this would be 1.00 moles for carbon in ratio to 11.1 divided by 7.39, 1.50. And so when we see 1.5 or something that's not a whole number, we're thinking, do I need a double, triple, quadruple? I just start going from the smallest multiple up. Obviously 2 works, so I multiply both these by 2 to get 2 moles of carbon in ratio to 3 moles of hydrogen. So the empirical formula is C2H3. And then the molecular formula is 4 times, or the molecular weight of the compound is 4 times the empirical weight. So whatever the mass is here, so 12.01 times 2, 1.008 times 3. I don't need to do this math. But if I wanted to, I'm just adding up that mass. So that'd be 12.01 times 2 plus 1.008 times 3. So that's 27.04 AMU, or grams per mole, times 4, 108.2. I'm only showing this part because another way we've seen the problem is we give you the molecular weight and then you divide the empirical formula weight into it to get the multiples. So if instead we said that the molecular weight's 108.2, what's the molecular formula? You'll be taking the 108.2 divided by the 27.04 to get that multiple of 4. So then we're taking the C2H3 times 4 to get C8H12. Okay, now there are other ways to solve the problem. I mean, the way we intend the problem, the whole point of the material and this questioning on the test is that in the middle of chapter 3, we present to you the percent mass to formula problem, and then we present to you the idea that we really want to know the molecular formula. So to get the molecular formula, once you know the empirical formula, if we tell you the molecular weight, you can get the formula. Okay. So the next question is kind of similar. It's a similar idea, but let's take a look at it. So we have a compound that's known to have the formula XCl3. So we just know that there's 3 chlorines in the formula for every 1 of X. And then if the compound's 79.8% chlorine by mass, what's the atomic weight and identity of X? Well, at first glance, this looks tricky. And maybe you've never seen a problem like this before. But let's just think about what we know about percent composition. What we know about percent composition is that the percent chlorine in this compound should be 3 times the atomic weight of chlorine divided by the formula weight of the compound. So whatever the formula weight is total for the XCl3, that the percent chlorine is just 3 times the atomic weight of chlorine divided by the formula weight of the compound. Like, this is just what I know. Like, I know this from what percent chlorine means. And so then this is equal to 79.8%. Okay, and so do you see how we can solve for the formula weight of XCl3 from this information, from this equation here? Let's get rid of the 100% and change this to 0.798. So 0.798 is equal to 3 times 35.45 divided by the formula weight of the compound. So you see how we can do some algebra here. We can take the formula weight of the compound to be equal to 3 times 35.45 divided by 0.798. So I just multiplied both sides by the formula weight of the compound and then divided both sides by 0.798. Just to do the algebra to solve for this here. And so I do the math. Type right. 3 times 35.45 divided by 0.798 gives me the formula weight of the whole compound is 133.3. Now that doesn't directly answer the question, but do you see how once we know the formula weight of the compound, we can get at X's identity by just subtracting the mass of the 3 chlorines. So the mass of X, I'm just going to take the mass of XCl3 minus the 3 chlorines. So I take the 133.3 AMU and subtract 35.45 times 3. And I get 26.9. So 26.9 AMU is the mass of X. And then we can just go to a periodic table to see that that's aluminum. So aluminum corresponds with that atomic weight. Now, I don't know. I was going to say, can we look at the choices and roll any out? If you knew beryllium only formed BeCl2, but that's kind of maybe far out there for you guys to get. But occasionally I've seen a problem like this before. There's another version I've seen where one of the choices is like krypton or something, where it's like krypton doesn't form like a stable compound like this that you could get a % chlorine on. So if you're like, well, noble gases don't form compounds, maybe you can roll out one of the choices by that logic. That's how we can use just the idea. The only thing we're using here is the idea of what % chlorine means. And so you may have seen this problem, been confused on how to set it up, but we're just trying to put into place, into practice, the simple concept of what a % element means relative to a formula. It's just the number of that atom in the formula times its mass divided by the formula weight. All right, so we talked a little bit about mass spec. That's how we get some data on, for a given element, what isotopes it exists as. We could use that experiment to tell us what the atomic weights of each individual isotope are. The given isotope will always be close to a whole number. If you look at the mass number is always a whole number. So, and if you take the number of neutrons plus protons, you get close to a whole number. We mentioned in chapter 2 that if you took, for like say carbon-13, where carbon-13 should have 6 protons, its atomic number is 6, has 7 neutrons, the sum of the protons and neutrons being the mass number up here, that the mass of carbon-13 will be close to 13 AMU, but not dead on, not exactly 13 AMU. And then it's not exactly going to be just the sum of the 6 protons and 7 neutrons. So you can't just take the resting mass of the protons and neutrons and add them up. If you do, you'll get a number that's too high because of the stability of the nucleus. And that stability of the nucleus, that's a concept from like the nuclear chemistry chapter, like chapter 22, I think, in the book. Okay, now I just say that to kind of know that when we're told here that magnesium exists as 3 isotopes, a sample is measured using a mass spectrometer where the atoms were separated on their mass to charge ratio. This just means that we're creating like magnesium plus ions and then separating those ions by mass to charge ratio. And then they're going to separate by virtue of the different masses of their isotopes. And so then we're going to select the mass a spectrometer output that matches magnesium. Now, one of the keys is that if we look at the periodic table, the average is 24.3. So that's the one thing that this question wants us to do, is that the average atomic weight for magnesium is from the periodic table, and it's 24.3 AMU. And so that's one thing that we should know, is to be able to check that average on the periodic table. And then another thing is that the atomic weight should be pretty close to whole number multiples. Like if I look at this here, where it looks like a mass is coming at about 24.5 AMU, that just cannot be. That's not an acceptable or what we would find for an atomic weight of an element. It should be close to a whole number. So you should see atomic weights close to whole numbers for atomic weights of atoms or for elements. And then we can roll out 4 because the average should have been 25. So if the average atomic weight of magnesium was 25, then 4 might have been correct. But since it's not 25, it's 24.3, we can roll that one out. So we're just kind of looking at which of these averages kind of give us an average of something that might be close to 24.3. We can roll out 2 as well, because it again would average out to be about 25 AMU, because we'd have about equal portions at 24 and 26. Most of our abundance of 25, the average would have been close to 25, so that's not going to be the correct answer. The correct answer would be the case where we have mostly 24 and just a little bit of 25 and 26. And so if we have a little bit of 25 and 26, that'll push the mass to be a little bit higher than 24, close to the 24.3 that we know for this element. So this problem here, to be fair, not my favorite problem, like not one that I wrote. Like our tests, if you didn't know this, are department-wide, so all the 1210 classes share the same exam. And so while these questions aren't my favorite style of question, the key details are checking a periodic table for the average, seeing which of the pictures kind of would give you that average just from doing some basic kind of thoughts of the arithmetic of the averaging out of the spectrum of the graph of the information, and then ruling out the case where the masses are not whole numbers or close to whole numbers. Okay, so this is what we call a particle diagram question. So this is showing us a reaction kind of picture, a glance of a reaction occurring inside of a container. So we have nitrogen gas, hydrogen gas, N2 plus 3H2 goes to 2NH3 is the reaction that these molecules are going to undergo. And so the N2s, we have 3 N2s, and then we have 1, 2, 3, 4, 5, 6 H2s, according to this picture. Because again, we can mix together whatever ratio of N2 and H2 that we wish, and we're just going to be limited in how much reaction can take place based upon the limiting versus excess reactant problem that can then ensue. And so what we can do here, it's going to ask us, well, which of the boxes here, so based on the initial amounts in the figure above, what is present after the reaction goes to completion? And this is that thing I was mentioning last time, based on the theoretical yield. I don't understand why they word it that way. It's just the based on the theoretical yield just means assuming the reaction goes to completion. So assuming your reaction goes to completion, we would be lassoing out, if you will, 3 H2s and an N2 together. So let's do that here. And so that'll give us the loss of those and replace them with 2 NH3s. And then we can do that one more time. Have 2 NH3s form in place of those molecules. And so we should have a box that has 4 NH3s and then the leftover N2 in excess. So I'm looking for a leftover N2. And then I'm looking for 4 NH3s. And then that shows a leftover H2 and N2. That's not correct. We don't have any leftover H2. And then this here, I think what this is getting at is the 2 NH3s aren't connected. So when we say 2 NH3, that just means NH3 number 1, NH3 number 2, and that they're not bonded together. If the 2 NH3s were attached together, then the formula would have been N2H6, like ethane is, C2H6. So this would look more like N2H6, which is not the formula of the product. It's 2 NH3s. So we have to, and again, sometimes this isn't entirely obvious, but what we mean by 2 NH3s is the same thing that we meant by 3 H2s, that completely separate molecules. So separate H2s for reactants, separate NH3s for products. So again, box 3 would be the answer to this question. So this reaction here, so chromium plus oxygen goes to Cr2O3, 39 grams of chromium, 16 grams of oxygen. Based on the reaction going to completion, based on the theoretical yield, which reactant remains and in what amount? Okay, so our options here could be converting to moles, making a BCA chart. I'm not going to do that, but that is a good option. That's not a bad one. Just might take a few more moments of time. A lot of times when we see the limiting reactant problem, students will often say, well, let me figure out the limiting reactant first. Let me make the product. So I see a lot of times students on this question will see how much Cr2O3 can you make with the one reactant and then with the other. That's not a bad way. That will tell you the limiting reactant if we analyze the data correctly, but it's going to end up causing us to do more math steps than needed. What we could really take advantage of here is trying to solve the actual problem along with the limiting reactant step at the same time. Why don't I just ask the question, how many grams of one reactant do I need to fully react with the other? Because if I get lucky, then I'll find out how much, if I get lucky and choose the limiting reactant, I will find that I need to react with a lesser amount of the other than what we have given, and then can solve the question of how much of it remains. And so now, based on the 4:3 ratio, if we could pick the limiting reactant, then we'll save us a math step. So if we can just magically pick the limiting reactant, we would save ourselves some time here. And so I'm looking at, I need 4 chromiums. The mass of chromium is 51. The mass of oxygen is 32. I'm going to guess here that, that chromium is the excess reactant. So I'm going to guess that oxygen is the limiting reactant. I could be wrong, but I'm just going to try and make an educated guess, because if I'm right, I save myself a dimensional analysis step. So I'm going to try to calculate the number of grams of chromium that I need to react with the 16.00 grams of O2. And if I'm wrong, I just figure out the mass of O2 that reacts with the given chromium. So we got 32.00 grams per mole of O2. For every 3 moles of O2 that react, we need 4 moles of chromium to react together with it. So we're just looking at our 3 to 4 ratio here. So 1 mole of chromium, 51.996, call it 52.00 grams. And I was right on my guess. So like 34.67 grams of chromium will react with 16 grams of oxygen. I've mentioned before that the dimensional analysis steps just require us to do the thought. They just require us to do the thought that, like, we're thinking if this amount reacts, so this amount is reacting, then this amount of chromium reacts with that oxygen, because they're both reactants. And so 34.67 grams of chromium reacts. We had 39 grams available. So the remaining chromium would be our 39.00 grams initially present minus the 34.67 grams that reacted. So that's 4.33 grams. So which reactant remains and in what amount? Chromium remains, 4.33 grams of it. Now just to stress, if we could have started with chromium in excess, or we could have started here with chromium and converted to the O2 that needs to react with it. If we had done the problem that way first, we would have seen that more than 16 grams of oxygen was needed. Now, occasionally, you get that, like, let's say it's 18 grams. Like, let's say we run through the calculation, we need 18 grams of oxygen. It's not uncommon for us to do 18 minus 16 equals 2, just because that gives us a positive number. So just know that we just have to have our thinking caps on when we're doing dimensional analysis. This is why I would say, if BCA charts are confusing, let's beat them into the ground until they're not confusing, so that we're thinking of them even as we're, like, solving a dimensional analysis step. So the BCA chart is kind of really what's in play here by the two reactants reacting together, and that's what's really being thoughtful here for doing the subtraction for the initial minus the reactant. Okay, so this takes us back to chapter 1, this problem here. So it says with no conversion factors that are going to be given, let's say, let's try to convert the volume of a pool in liters using the dimensions 5 meters by 8.5 meters by 2.5 meters. Now, I will say that there's one conversion factor for converting volumes that's given on the test, and that's 1 cubic centimeter is 1 milliliter. Like, so this is the only thing that we really give you on converting volume units through, like, a cubic length unit. Now, what we could do, and so it does say with no conversions given, but this is the one given. That's so obvious that I think we all know this one already. So this is really the only conversion factor we're going to want to use. If that's the only conversion factor I have available, why don't I just convert these to centimeters? So if those are all centimeters, converting to centimeters, then I will calculate the volume in cubic centimeters. So let's do 500 times 850 times 250, and that gives me a value directly in cubic centimeters. Now, sometimes this is a helpful trick, sometimes it's not a helpful trick. If you're using one of these calculators, you can go second, scientific, and switch over from floating to scientific mode. So it'll say it's 1.06 times 10 to the 8, as opposed to a bunch of zeros where we have to count. If you want to switch back, just go back to FLO for floating notation. And most calculators have the option of switching between scientific notation and, like, the full number notation. So 1.06 times 10 to the 8 cubic centimeters, that's equal to a milliliter. So that's 1.06 times 10 to the 8 milliliters. And then to convert to liters, 1,000 milliliters in 1 liter. And so divide by 1,000 will be 1.06 times 10 to the 5. to convert to liters. Now, had we left it in meters, it's not wrong to go 5 times 8.5 times 2.5. Let's say we did it this way. We come up with 106.25 cubic meters. If you're doing this step here, 1 meter to 100 centimeters, the key is you have to cube that conversion factor. So you have to cube the 100, cube the centimeters, cube the meter. That'll give you the 1.06 times 10 to the 8. Then we convert that back over to liters. So if we had done the math in cubic meters and we want to convert to cubic centimeters, you just have to cube the conversion factor for that cubic unit. That's what we were doing by converting to centimeters before we multiplied. All right, there's some more here. We'll get into these other review problems on Monday. Feel free to look at them ahead of time. If you have questions, feel free to email me over the weekend. And go Bucks, and happy studying. Have a great weekend.